How's it going?
Good.
Good?
Yeah.
How's the weekend?
Boring.
Boring. Sounds like I'm not giving you enough work then.
Yeah.
Didn't watch the Super Bowl?
Well, I was watching we were watching the Super Bowl at my grandma's house, and then we left and we were like, oh, the 49ers got this. And we got back and it was 24.
Uh-huh.
20.
Yeah. You can see that.
That was exciting.
Yeah.
I mean, that's the exciting part.
Yeah. Commercials I thought were disappointing. There were a couple I was amused by, but in general I thought they were disappointing. My opinion.
Yeah.
How goes it? Questions about anything before we get going? Okay.
Can you go over again, like, how we know when a problem has, like, no solutions or one solution that infinitely many?
Okay. So, just to draw. All right, so here's three matrices that are in reduced row echelon form. I made the system to have three equations, three unknowns, but the same idea is applicable to any size that we would have. Right. So how many solutions does the first equation, or the first system have?
One.
Exactly one, right? Because if I read off the equations, I see it says x1 equals 3, x2 equals 2, x3 equals 5, or negative 5. So we get exactly one solution if we get a pivot in every column. That tells us exactly one solution. Because we literally see variable 1 equals a number, variable 2 equals a number, and so on down the line. The second system that I wrote down, we do not have a pivot in every column, and similarly, in this system I wrote down, the third one here, we do not have a pivot in every column, right? So as soon as we get no pivot, or a column without a pivot, that will correspond to a free variable if applicable. So that tells us that we're either going to get no solution or infinitely many as soon as we see a pivotless column. Because I can't write down the equation variable equals number at that point. Because I don't have a way to have that variable all by itself. So the difference between the two is what? What does this last equation say here? 0 equals 0 versus this one says 0 equals 4, right? So if I have 0 equals 0, that's fine, right? But if I have an equation that tells me 0 equals something that's not 0, that's false. So this one has no solution. So that's how I can tell the difference between the no solution case, which is that one that's up in the upper right-hand corner, and the infinitely many solution case where I don't have a contradiction. So when you do if you do the row reduction and you get a contradiction, that's when you have no solution. And in this case, if you did the row reduction and got to this point, you don't have a contradiction, so you know you have infinitely many solutions, and you do the thing with the parameters. Does that help?
Mm-hmm.
Cool.
And then for number 26,
Which page? I'm sorry. I don't remember what. 20, thank you.
are we supposed to use a matrix to solve that?
26. Find the coefficients A, B, C, D? Yeah, you should use a matrix.
Okay.
So they gave you 3 points on the circle.
Mm-hmm.
So those points are supposed to satisfy the equation. So what you're trying to figure out are the A, B, C, and D. And since there's only 3 points on there, you're going to end up with you'll end up with infinitely many solutions because you only get 3 equations with 4 unknowns. So you just have to pick some. Pick a specific, and what that means is when you do this, when you solve the system, you'll get a free variable. You'll have to because you don't have enough information to get all the exact values. So just pick a value for t, and then whenever you write down the solutions, and that'll give you what you need for A, B, C, and D. Because remember, when we write that in terms of the parameter, that says that any t will work. So I would just use t equals 0.
So do the points go in the matrix?
The points go into the, you want to set up the system before you do the matrix. So you've got x, y coordinates.
Mm-hmm.
So one of them is -2, 7. And you're trying to fit the equation ax squared plus ay squared plus bx plus cy plus d equals 0. That's what you're trying to solve, right? So you want to plug this in for your x and this in for your y. And so then you'll get an equation with a, b, c, d.
Mm-hmm.
And so you'll do that for all 3 points and plug it in. Does that make sense?
Mm-hmm.
Okay. Other questions? Well, let's continue on then with our rules of arithmetic. Start talking about inverses a little bit. Start doing some other properties. Let's just go through. I want to go through one more example with proving one of the properties of arithmetic. So this is actually property C in that theorem 1.4.1. And it says that AB, no, it doesn't write it this way. A times the quantity B plus C is AB times C. So what property are we trying to prove here? What's the name of this property as far as multiplication goes? As a name. Commutative means that you can flip it around.
Distributive property.
Distributive means you would be going over a sum. You got good words, just not the right ones to apply to this one. What else you got? Long word starts with A.
Associative.
Ah, it's associative. Yeah, we're regrouping, right? This is the associative property. We're reassociating by grouping. So commutative is like you commute to work, right? You go back and forth. That's where the commutative idea comes from. Not communicative. You're not a hippie. Not communicative. It's not the coronavirus. Okay. Commutative. All T's. No N's in the word commutative. All right. So anyway, let's talk about how we would prove this. So same idea as we did last time. We're going to take a general element. We want to see what a general element on the left-hand side looks like, see what a general element on the right-hand side looks like, and show that they're the same. Okay? So we'll start with, we're going to let A have some general entry, B have some general entry, and move that comma over a little bit, C have some general entry. Now I want to make sure that I can actually do this operation. So if I start with A being an M by N matrix, what size better B have? And by something else, some P. And then what better C have? P by something else, right? So I'll say R. I could have said Q, but I decided against it. The letters don't matter as long as they're different. Well, and the same where they're supposed to be, right? You can use Greek letters, you can use emojis, it doesn't matter what. As long as you have symbols in there for something. Okay, so Remember that for two matrices to be equal, they need to have the same, all the entries have to be equal and they have to have the same size. What is the size of both of these going to be when we're done multiplying? Check that first. What size will we have when we're done?
M by R.
It'll be M by R, right? Think about it either way. This one says do B times C first and then do A. So the left-hand side says, right? B, we said was N by P, and C is P by R. So BC will be what?
N by R.
N by R. And if I do M by N times an N by R, we'll get M by R. And then you can do the same analysis for the other one, right? This will be M by P times a P by R, and then we'll get a M by R again. Everybody see that? I went through it quickly. Are we okay with that? Matching those things up? All right. So they're both M by R matrices, which is important, right? Because they need to have the same size. Just checking that first. All right, so now let's work with the left-hand side and the right-hand side. Notice we're trying to find a general entry on the left-hand side, so I want to work inside the parentheses and then out, right? So let's do B times C first. Let's call it a D, bless you. Let's call it a D sub ij. We said that this is going to be N by R. What does a general entry look like when we do the product? How do we do a product of matrices?
Just B sub ij times C sub ij.
Do we multiply entry by entry when we do?
Multiply row by column.
You do a row by a column, and then what do you do with all those products? Add them, right? So I have to do a sum, right? All right, so remember that we have to match row to column, so we have to go from 1 to the number of columns here, rows here. Those are the things that match up, right? So our upper will be P in this case. Our upper limit for that sum will be P. And then we'll take B sub I K, C sub K, J. Remember again, the B sub I K is representing that we're running across the ith row. And then the C sub Kj is that we're running down the kth column. So that's just what the general entry looks like for B times C. Now things get a little dicier because I have to do the A times the B times C. And this is another product. This is one of the reasons why I want to do this one, is just to talk about how we keep track of these. We'll do another example here in a minute that'll be a little bit, hopefully it'll be a little bit easier. So what does our F sub ij have to look like? What two entries are we multiplying together? Well, the F is going to be our general entry, right? So you're right. The D is going to get multiplied. The A, right? The A and the D's are going to get multiplied together. So it's the general entry of A and the general entry of BC, right? Now again, it's a product, so when we do a product, we have a sum again, correct? I don't want to use the same K, because this index that I'm going to use here does not have anything to do with the index here. Okay, so I'll call it L, for lack of a better letter. This is going to go from 1 to N, right? because the n is the matching piece, right? A is m by n, BC is n by r. So the n is the matching piece. And then it's A sub I L, B, not B, D sub L J. Right? This is the piece that matches in the middle. Okay? But now I should be able to plug something in for D. How do I get D sub Lj? Well, where is my D defined? Just above, right? It's here, correct? What's the difference between these two things? Yeah, the L and the I. The I's are replaced with an L, right? Well, if I look over here, what should I do with this I? Turn it into an L, and everything else stays the same, right? So this will be the sum from K equals 1 to P of B sub Lk, C sub Kj. Right? Lots of little things to keep track of. I know these aren't necessarily the most fun things to do. But it's an important, like I said, this is an important skill. It's the idea of us doing this stuff is not only to verify that these properties are true, but it's the skill of understanding how we're proving equality here. It's the proof technique that I'm more interested in than anything else. Okay? So if you ask me, when am I ever going to do this in another class? Well, unless you're going to do more proof classes later, where you have to do this kind of thing, well, not necessarily. But the idea of understanding how to do this kind of proof does pop up. Okay? And if you ask me, well, what am I going to use this in the real world? You're not. Unless your real world is getting up here and teaching other people on your algebra. You're not. It's not going to come up in the real world. Okay? But the idea of being able to understand the equality of things, that does pop up later. Okay? Verifying these ideas. So, yeah.
So what is the I subscript mean here?
The I subscript and the J subscript?
Yeah.
So we're trying to do this generally. So the I subscript is that we're saying we're in row I of this matrix, and the J is we're in column J. So if I want to know what the I entry in this particular matrix, if I want to know what the entry is in row I and column J, it looks like this.
Oh, hang on.
It looks like a mess, but it looks like this. That's the I and the J in this particular case. So this is now we just have real numbers here. So this is a number out in front of this sum. So we have a property that says I can do something with this number. I can do what with it? They can distribute it. There's the distributive property, right? I can rewrite this as the sum L equals 1 to n, sum from K equals 1 to P of A sub I L times B sub L K C sub Kj. And I purposefully put those parentheses in there. Now with real numbers, when I do this multiplication, typically if you wrote this out, would you bother even putting these parentheses in here? No, because what do you already know is true about real number multiplication? They knew it, so they have an associative property, right? So usually we just leave it off. If we have an A times a B times a C, we would just leave the parentheses off because we already know it's associative, right? Before we started this mess, we don't know that matrix multiplication is associative. So far so good? All right. Not a lot more I can do with this except for play with parentheses. There is one more thing I can do, but we'll do that in a second. So I should probably go ahead and look at the right-hand side and see what happens. Let's look at the right-hand side. On the right-hand side, the AB is in parentheses first, right? Yeah? Okay? So, general entry here. This one's an M by P. Not that that's necessarily that important right now. All right, so same idea. We need to run across the rows of A, run across the columns of A, and down the rows of B and match it up, right? So our summation, I'm going to go back to the same letters maybe I won't use the same letters. Let's use a different letter. I've already used K and L and M and N and P and R. So I guess I'll use an S. Where does this one end? N, right? It goes through the column. It goes through the columns of A and the rows of B, which is N, right? Okay. We're taking A sub what? IS and B sub SJ. Good. Good news is we're almost done. Which is good because we're running out of letters pretty quickly. Okay. All right, this should be the last, well, you should have one more new letter we need to do. All right, so now let's add in the C. Which two general entries do we want to multiply first together? What letters do we want to use? For A, B, we want to use G. For the C, we want to use C, right? So we want to do the C's and the G's times the C's first. Much like we did here when we did the A's times the D's first before we plugged in. Same idea, right? So I need a summation. I'll use a T for my index this time. Where does that sum stop? I think it goes up to P, right? Because the P is the match in between those two. Right? Okay. And then it's, what goes first? G sub I T, right? Because it's the thing, it's that one. And then what goes second? C sub TJ. I promise that's the last new letter we'll have to do. Okay? It's the last one. All right. Which of those two things can I plug something else in for? Yeah, I can do the G, right? What can I put in for G? Okay, so this is my G, right? So, yep, so it's a summation. S equals 1 to N. I agree. It's A sub I T. Well, hold on. Nope, it's not there. I sub I S, B sub S T. The reason why is this is the, what's the difference between this G and this G? The J has been replaced with a T, right? So I go to the right-hand side and I replace the J with a T. Or remember, I don't worry about this side to start with. Okay? Think of this as a function where it has two inputs. I can put in an I, I can put in a J. This says put in the T for the J. So then I look at the right-hand side and I put in the T for the J. Think of this, if you think of the subscript as a function, it's literally just putting in a different input. All right. Now I purposefully put parentheses around that summation because that C sub Tj is not inside the summation yet, right? However, what can I do with that C sub Tj? Distribute it inside, right? So then we can write this as the summation t equals 1 to p, summation s equals 1 to n of a sub I s, b sub s t, c sub t j. Okay, now that we're done with playing with the letters, what are we trying to argue? What two things need to be equal? This one and the one that's up in the upper left-hand corner of the screen right now, the F, right? The F sub ij and the H sub ij need to be the same. All right, tell me what looks different about them right now.
The letters.
The letters look different. In particular, which letters look different?
L, K, and T, and S.
Okay, so the L and the K and the T and the S look different, right? But they're all in the same relative spots, right? Okay? I got an L, I got an S. I got an L, I got an S, right? I got an L, I got an S. They're all in the same relative spots, right? Same idea for the other one. I got a K, I got a T, I got a K, I got a T, I got a K, I got a T. Okay? So the question is, do the letters matter? Could I just change the letters? Yeah. If I made T, say, a smiley face, and the K a smiley face, do I get the same expression? Right? And do the same thing with the S if I made it, I don't know, poop emoji, whatever you want to do, right? In both of them, I would get the same expression, right? The only other difference is the grouping. Right? Okay. So those two things really are the same thing. Because we know that we can regroup because real number multiplication is associative, right? So just write it this way, identifying L and T, oops, sorry, not L and T, L and S, and, or I should say L with S, and K with T, we notice, there is one more thing I should mention. We notice that F sub ij is equal to H sub ij. There is one more thing that was different about them. What was the one more thing that was different about them? Scroll back up for just real briefly. What other thing is different about them besides those letters? The order of the summation's reversed, right? So the question is, can I reverse without any issue? I can for two reasons. One is that this is real number addition, right? And real number addition is commutative. The second is that this sum has nothing to do with that sum. If this went from 1 to t, I couldn't just flip it out in front, because then I wouldn't know what the t is out in front. Remember, if you've had Calc 2 or Calc 3, you did double integrals, right? And remember, if the inside integral had a variable as one of its limits, you had to rewrite that was a weird way to say that word. You had to rewrite the region, right? You'd have to do the same thing for a sum. If one of the sums depended on the other one's index, it's the same concept, right? You can switch them around, but you would have to change the indices. The limits on your sums would change just like your limits on your integrals did. Okay. But remember, if you had numbers for both x and y in your double integrals, did you have to worry about it? No, you could just flip it, right? If you had a rectangular region, it didn't matter. It was when you had those non-rectangular regions, if you were trying to reverse the order of integration, you had to worry about changing your limits. The same thing would be true here, but we don't have that problem because we're going from 1 to n, which is fixed, and 1 to p, which is fixed. N doesn't depend on t, p doesn't depend on s. So anyway, identifying those things, we notice that the f sub ij is equal to h sub ij, so a times bc is equal to ab times c for all a, b, and c that can be multiplied. What I mean by that is that have the right dimensions. I know that was a longer one to suffer through. I don't disagree. But we'll play around with this idea a little bit more with things that aren't so difficult to deal with. All right. So let's talk about a specific type of matrix that has to do with multiplication. And we're going to refer to it as the identity matrix. It's interesting that we actually say a lot of times the identity matrix. There's actually more than one. There are infinitely many identity matrices, depending on the size. So what we mean for the identity matrix is the same idea that we talked about before. And this leads up to one more property that we'll talk about here in a minute. But again, linear algebra, any algebra, has its roots in solving equations, right? So again, if I talk about, you don't have to write this part down, just illustrating why we care about an identity matrix. If I want to solve the equation 3x equals 9, there's a lot of work that actually goes into this besides you just telling me it's x equals 3. Okay? There's a lot of work that goes into this. For first, I have to understand that I can undo multiplication by 3. Right? Which means there has to be a multiplicative inverse with respect to the 3, right? There's a lot, that's one important property, right? I have to be able to undo multiplication by 3, right? But notice that when I multiply both sides by a third, really I've got a third times 3x, right? Why did I multiply 1/3? I want to cancel out the 3, right? To be able to cancel out the 3, I have to be able to reassociate, right? I can't cancel out the 3 if I don't know that I can reassociate, correct? Now, why did I choose to multiply both sides by 1/3? Because I could have multiplied both sides by anything I wanted to. Why did I choose 1/3? To make this a 1, right? Because why did I want this to be a 1? Well, what do I know that 1 times x is? X. So this 1 here is the multiplicative identity. By the way, this is why when kids start learning how to do self-equations, it's hard. For us, we've done it so many times, this is pretty, I mean, we say x equals 3, we're done, right? But think about someone who's never seen this before. There's a lot of math. A lot of hard concepts, right? This is why even what they call one-step equations, which is what this is, it's not really a one-step equation. It's such a lie. Look how many steps we had to do, right? You know, I mean, when you talk about this with kids, you don't do this, but there's a lot in there. That's why they struggle, right? It takes some time to get to understand what you're really doing here. All right, the end of this part, though, is the part that I'm interested in. Also notice that we needed associativity to do this, which is another reason why we need associativity of matrix multiplication, if we want to be able to undo matrix multiplication. Okay? This is the step that I wanted to talk about. The reason why we got to 1 is because this 1 times this x needed to be this x, right? Okay. This is where the identity matrix comes in. We talk about the identity matrix. When we say that, we mean the identity with respect to multiplication. There's certainly an additive identity matrix. It's 0, right? If I add the 0 matrix to anything, I get 0. Again, I have to have the appropriate size. You can guess what the 0 matrix has to be. It has to be all zeros, right? If I'm going to add the 0 matrix to something and get that same matrix back again, it has to be all zeros. The identity matrix, when we say the identity matrix, we don't mean addition, because we think of that as the 0 matrix and it's just a bunch of zeros, okay? When we say identity matrix, we mean multiplication. So we have to have an idea of what this has to look like. Now, if you think about the 0 matrix being all zeros, you might think, oh, I'll just use all ones. Be a logical first guess, right? If I use all zeros when I add, why wouldn't I use all ones when I multiply? It's a logical guess, correct? Do I get... Now remember, if this is supposed to be an identity matrix, what should I get back when I'm done? The same thing, this thing, right? Do I get that back? No, what do I get? Get A plus C, B plus D, A plus C again, and B plus D again. Right? Definitely was not what we started with, was it? Not unless A, B, C, and D have some special properties, but it's definitely not what we started with, right? Okay. So that can't be the identity matrix, so that guess was wrong. All right, so let's think about what we would need. I want to get back the same thing that I started with when I multiplied, right? So if I take this row and multiply by this column, I want to get back an A and a B up here, correct? And I don't want anything to do with the C and the D. Well, let's handle that part first. If I don't want anything to do with the C and the D when I multiply this row, what should this entry right here be? That would be 0, right? That kills off the C and the D, doesn't it? If I take this row and match it with that column, it'll kill the C and the D. So I want this to be a 0. And then if I want an A here and a B here, what better this number be?
1.
A 1, right? Because I need to multiply by the 1. Likewise, in my second row, I want to make sure I keep the C and the D and eliminate the A and the B. Well, to make sure I eliminate the A and the B, what better this entry here be? 0. And then to keep the C and the D the same, that better be a 1. Okay? So, oops. If you take the 1, 0, 0, 1 and multiply it by the A, B, C, D, you get back A, B, C, D. That worked great. Okay? But with matrix multiplication, we have to be careful because we also know that multiplication doesn't necessarily work both ways, right? We want this identity matrix to work on both sides. So we should also check that we get the other way around, which in this case we do. So if I take A, B, C, D, and multiply by 1, 0, 0, 1, I really do get the same thing back again. We want this identity to work on both sides, and we have it, especially when it's square. We want this two-sided identity idea. So it does work on both sides. All right. Now, again, to be able to have this work appropriately, we need to make sure that we end up with the same matrix back again, so we need to make sure we have the same size. So our identity matrix here always has to be square, and it's going to change by size. Okay? So when we do what we refer to as the n by n, always has to be square. The n by n identity matrix, the notation we typically use is I sub n. The reason why we only use one subscript for the notation is because it has to be square. So if I know what n is, I know it's an n by n. Okay? Well, if I just write it out longhand, ooh, hey, that was a funky looking bracket. We get 1 on the diagonal, and then we get zeros everywhere else. This is a special type of what we refer to as a diagonal matrix. We'll talk about diagonal matrices later. But you can see why they call it a diagonal matrix. It has, the only place where it has non-zero entries is on the diagonal. Everywhere else is a 0. They also give you definitions later on of what are referred to as upper triangular matrices and lower triangular matrices. Upper triangular would be that all your non-zeros are up here. Lower would be all the non-zeros are down here. We'll talk about those later. But this is an example of a diagonal matrix by what its shape looks like. Again, it has to be square. So I know that not only is this upper left-hand corner a 1, this lower right-hand corner is also a 1. Okay? If I were to write this out with general entries, this is why, by the way, I haven't been using E's, because E is typically used for the identity matrix. The reason why we use E for identity a lot of times is because it comes from the German. It stands for the German word for identity, which is Einheit. That's why we use E. There's a lot of reasons why we use letters that we use for different things, just because they came from different languages. Like, for example, I use the letter M for slope. Right? Y equals mx plus b. The reason why I use m is it comes from the French verb monter, which means to climb. So that's why we use. That's why those letters stick. Depends on what. Basically, it probably depended. I'm guessing. And this is a guess. I'm guessing it depended on whatever the prevalent book was at the time that everybody learned from. For example, Euclid's Elements. Euclid, the ancient Greek guy. Euclid's Elements was used to teach geometry. Until it was the book people learned from geometry until like the 1800s. And then there was some different advances for textbooks. So my guess is whoever started talking about identities to start with used the German. The German was the prevalent book text at the time, so that was why the E stuck. That's my guess. It's also why we use the capital Z for the integers, because it's the Zahlen is the German word for integer. In case anybody cares. You probably don't care. Anyway, we can define these by what they have to be. So again, the identity matrix has 1s down the diagonal and 0s everywhere else. What's true about the subscripts down the diagonal? What's true about I and J down the diagonal? They're the same, right? This is the 1-1 entry, this is the 2-2 entry, and so on down the line, right? So this will equal 1. If I is equal to j, it'll be 0 if I is not equal to j. So this is a more, I'll say, algebraic way to describe the identity matrix, because it's telling you where the non-zero entries, the 1s are. So far, so good? All right. So using this notation, you can actually prove that if I take the in times an a, I'll get a back again. So the theorem is the following. Oops. If I have an m by n matrix A, then if I multiply on the left by the m by m identity matrix, I get A back again. And if I multiply on the right by the n by n identity matrix, I also get A back again. I have to be careful with size, right? If I try to put im on the right, it won't work. The dimensions aren't correct. Right? Okay. So let's see how we would prove this real quick. Or as I'm lazy and I abbreviate proof to poof, we're going to poof it. Okay. So let's see what happens when we actually multiply. What do I want this to turn out to be when I'm done, by the way, by what we're trying to prove? Yeah, it should be just A, I, J, right? The entry should just be, when I'm done simplifying B sub I, J, I better get A sub I, J, right? Because the theorem says that this product should be this matrix. How am I going to write out the product? What letter did we use to denote the identity? What letter are we using to denote the general entry for IM? E, right? And for A, we're just using A. For a product, we know we have to use a summation, correct? K equals 1 to, what's the upper limit here? M, right? Because that's the number of columns in IM, number of rows in A, right? And then we have what inside here? E sub I. Okay, good. And A sub KJ, right? So again, this K is representing that we're going across the columns of I. This K is representing that we're going down the rows of A, right? Okay. What do we know about E sub IK? We know something very specific. It's still up on the screen. What do we know about E sub IK? It's either 1 or 0, and specifically, when is it 1? Yeah, when the I is equal to K, right? Or the K is equal to I, either one, correct? This I is not changing, but this K is, correct? Think about what you would get if you wrote out the sum. It would be EI1A1J, right? And then EI2A2J, EI3A3J, all the way up to EIMAMJ, correct? So if I just write that out longhand, to start with, it would be EI1A1J, EI2A2J, the last one would be EIN, I said E and wrote an A, EINANJ. I left a space, purposefully left a space. What's the important value for K in this whole thing? I, right? Somewhere in the middle here, I have an EIIAIJ, right? We agree? Somewhere in the middle we have that? Scroll that over a little bit. Just trying to blow it up a little bit since I was writing so little. K goes from 1 to N. I is somewhere in between there, correct? So somewhere in the middle, that has to be in there. What's EI1 then? 0. What's EI2? What's EIN? EII? 1, right? So this whole thing, if I write it out longhand, it's 0 times A1J, 0 times A2J, 1 times AIJ, 0 times ANJ. What does that simplify to? AIJ. Oops. It's a little low. Sorry. Is that what we wanted? It's exactly what we wanted, wasn't it? The only term that survives out of this entire product is the one that's multiplied by the EII, right? Because we remember for the identity matrix, we specifically put those zeros in there to kill off the other rows. It's the whole reason why they were in there. Right? So the only row that survives is the ith row, and so we get AIJ back again. So that proves what we wanted. Let's bring that back down there. That's exactly what we wanted, wasn't it? That IMA is equal to A? Precisely what we wanted. You would do the same type of proof for the second one. I would suggest practicing that if you're having some issues with getting these proofs down. This was a much shorter proof, by the way, all right? Okay, a lot better than the last one. Okay, I suggest practicing, see if you can get that other one. All right, we'll talk more about inverses next time. I'm also going to post a video, so I'd like you to watch that for Wednesday. I'll email you when it's ready. Have a good one. We'll see you on Wednesday.